Okay, so now we will do some more exercises. One. So let Hi I equals 1, 2, 3 be Hilbert spaces such that we have the continuous inclusions H1 in H2 in H3. Assume that the inclusion H1 in H2 is compact. A. Show that for every epsilon positive, okay, this itself is A. Okay, there exists C epsilon greater than or equal to 0 such that for every U in H1 we have norm U in H2 is less than or equal to epsilon times norm U in H1 plus C epsilon times norm U in H3. Okay, so if U is in H1, then it's in all the three spaces H1, H2 and H3. What we are saying is we can estimate norm of U in the middle space H2 by epsilon times norm U in H1. So we are putting a very small coefficient for H1, but then we pay a price. C epsilon will be somewhat large for H3. Okay, so this is the idea. Okay, so solution. Assume not, then there exists an epsilon positive such that for every n you have, there exists a U tilde n in H1 which violates this with the constant n. So however big a constant n you put for C epsilon, it will still violate. Okay, so norm Un tilde of H2 is bigger than epsilon times norm Un tilde H1 plus n times norm Un tilde H3. Okay, so we can normalize, and so you can assume that norm Un H2 equal to 1. Okay, and then therefore you have 1 is bigger than, so you divide throughout by norm Un tilde in H2. Okay, so that will give you a new vector Un, so that is Un by norm Un tilde by norm Un tilde H2, that will have norm 1 in H2. So 1 is bigger than epsilon times norm Un in H1 plus n times norm Un in H3. Okay, so this will imply that norm Un in H1 is less than 1 by epsilon, so it is bounded, and if you want, and then norm Un in H3 it goes to 0 because it's less than 1 by n, and therefore it goes to 0. So you have, we are in a Hilbert space, we have a bounded sequence in a Hilbert space, so there exists a subsequence, again denoted UN. I have done this often, so I am going to work with that subsequence, so I don't want to put the UNK and so on because I am not interested in the original sequence anymore. So again I will define it as UN such that UN converges to U weakly in H1. Okay, but then H1 to H2 is compact, so H1 to H2 compact, so weak convergence becomes strong, So un goes to u in H2, and therefore obviously un will go to u in H3. But norm un goes to 0 in H3, and this implies norm un H3 goes to 0, so implies un goes to 0 in H3, and therefore u equal to 0. Okay, so un goes to weakly to u in H1, weakly to 0 in H1, in norm in H2, and also in norm in H3. But this is a contradiction, since norm un2 is 1 for all n, so it can't go to 0 in norm. Okay, so this is a contradiction, and therefore we have that the inequality is valid. So B, omega in Rn bounded open set of class C1 given epsilon positive, show that there exists a C epsilon which is positive, such that for every u in H2 of omega, we have norm u in 1 omega is less than epsilon times norm u in 2 omega plus C epsilon times mod u in 0 omega. Okay, so solution is one line. So you have H2 of omega is continuously included in H1 of omega, and that is completely in L2 of omega. And then we have seen by Relic Kondrasov, in fact both these inclusions are compact. This one is compact by Relic's theorem, and this by iteration we said that every Wm plus Hm plus 1 will be in Hm compact, so apply A. Okay. Then C, prove same inequality in Rn. So now no longer you can use the previous theorem because you do not have compact inclusions, and show that C epsilon can be taken as C times epsilon power minus 1. Okay. So let u belong to H2 of Rn, and then we want to look at the H1 norm. Okay, so integral on Rn 1 plus mod xi square, we are going to use the Fourier interpretation, mod u hat xi square d xi equal to integral some mod xi less than eta plus integral mod xi greater than or equal to eta. Okay, so that is equal to integral mod xi less than eta of 1 plus mod xi square of mod u cap xi square d xi plus integral mod xi greater or equal to eta 1 plus mod xi square whole square into mod u cap xi square by 1 plus mod xi square d xi, which is less than or equal to mod xi is less than eta, so 1 plus mod eta square into integral over Rn mod u cap xi square. So we have got the L2 norm here, plus again mod xi is bigger than or equal to eta, and therefore it is in the denominator 1 by 1 plus eta square. Okay, mod eta square if you like, but eta is non-negative, so the modulus is not necessary. So here also let me just write eta square. Okay, 1 plus eta square integral on Now I am going to write integral on Rn because I am going to mod xi greater than equal to eta is what I have to write. I am going to write a bigger integral 1 plus mod xi square whole square mod u cap xi square dz. Okay, so you get that norm u square 1 Rn is less than or equal to 1 plus eta square mod u square 0 Rn plus 1 by 1 plus eta square integral I am sorry norm u square 2 Rn. So a square plus b square less than or equal to a plus b whole square, and therefore you have norm of u 1 Rn less than or equal to root of 1 plus eta square mod u 0 Rn plus 1 by root of 1 plus eta square norm u 2 Rn, and then you take 1 by root of 1 plus eta square equal to epsilon. Okay, and then you are done. Second one. So omega contained in Rn open set and E contained in omega arbitrary subset. So we define capacity of E with respect to omega. So we write this as cap of E. So you should put an omega here, okay, cap omega of E, but I may drop it when I am talking only of. So this is the definition. Inf of integral over omega mod grad u square dx, where u is in h10 of omega and u identically 1 in a neighborhood of u. So this is called the capacity. Sometimes it's called the electrostatic capacity because this comes from the theory of electrostatics, and in fact these functions will come there. So there is a condenser in the center, the E will represent a certain condenser, and then around it you have an electrical field, and this is the kind of functions which we will study there. Okay. So A, if E is contained in F is contained in omega, this implies cap. So I will drop the omega now. So cap E is less than or equal to cap F. So this is obvious. If U is in h10 of omega, U identically 1 neighborhood of F implies U is identically 1 in a neighborhood of U. And therefore you are taking the infimum of a bigger set for E, so the infimum will be smaller, and therefore this implies that cap E is less than or equal to cap F, just from the notion of an infimum. Now cap E equals inf of cap omega prime such that E is contained in omega prime contained in omega, omega prime open. So obviously cap E is less than or equal to cap omega prime for all E contained in omega prime contained in omega, and therefore cap E is less than or equal to infimum of cap omega prime. Omega prime contained in omega, E contained in omega prime. So one inequality is clear. So we have to show the reverse inequality. So let epsilon be greater than 0. So by definition there exists omega prime open neighborhood of E. So E is contained in omega prime contained in omega, omega prime open. okay, such that integral u is identically 1 in omega prime and integral of omega mod grad u square dx is less than cap E plus epsilon, because that is the definition of the infimum. Okay, so cap E is the infimum, so we can find one which you can do like this. Okay, so now because u is 1 in omega prime, that's the neighborhood of omega prime, its omega prime is an open set, and therefore this implies that cap of omega prime, which is the infimum of such functions, is less than cap E plus epsilon, and that proves the result. So we have that in fact the infimum is equal to the whole thing. Okay, C omega in Rn bounded open set, there exists a C greater than 0 such that for all E contained in omega, you have measure of E, this is the Lebesgue measure of E, is less than equal to C times capacity of E. So this capacity is something like the measure, okay, it is comparable to the measure, so it's another kind of measure of a set. How big a set is can be found in a different way. Okay, so we have U identically 1 in a neighborhood of E, U in H1 0 of omega. Let us take any such function. So then you have mod E is less than equal to integral on omega mod U square dx, because mod U square over omega is greater than equal to mod U square over E, and then it is identically in a neighborhood, so it's 1, and so that is equal to mod E. Okay, so this is trivial, and now by the Poincare inequality, this is less than equal to C mod grad U square dx, and this is nothing but Poincare's inequality. So this is true for any such U, so you take the infimum, so mod U is less than equal to C times capacity of U. Okay, so that these are some elementary facts about the capacity. 3. So let omega contained in Rn be a bounded open convex set, and let 0 belong to omega. Let 0 less than lambda less than 1, then define lambda omega equals set of all lambda x, x is in omega. So 0 is in omega and any x is in omega, so lambda x for all 0 to lambda, it's will be in omega itself, so this is contained in omega. Let 1 less than equal to p less than n. Let u belong to w1 p 0 of omega mod u 0 p star omega equal to 1. So we choose such a function. You can always find, you can find any u which is non-zero, divide it by the LP star norm, because W1P is contained in LP star, and that will have norm LP star 1. So define uk of x equals k power n minus p by p u of kx if x belongs to 1 by k of omega. Because if x belongs to 1 by k of omega, kx will belong to omega, and therefore you have that this is well defined. Okay, 0 if x belongs to omega minus 1 by k omega. Okay, then show that uk belongs to w1k 0 1p 0 omega mod uk 1p omega equals mod u 1p omega for all k, and mod uk 0 p star omega equals mod u 0 p star omega for all k. Deduce that W1P0 of omega included in LP star omega is not compact. So here we have an example, explicit example of a domain which is a convex open set containing the origin, where W1P0 omega and hence W1P omega also in LP star is not compact. We saw in the Relic-Kontrasov theorem the LP star was excluded. Okay, so solution. So integral on omega mod grad uk of x power p dx is integral over 1 by k omega, that is where it is not 0, k power n minus p, because by p I have taken the pth power, mod grad u of kx power p dx. Okay. And then because I am differentiating, I will have to another k power p, because u of kx has to be differentiated. So this is, I have just got, I will pick up a k every time. Okay. So now if you make a change of variable kx equal to y, then k power n dx will be dy, and therefore this will be equal to, and this k power minus p and k power p would have got cancelled. So this will become integral on omega mod grad u y power p dy, which is equal to mod u 1p omega. Integral on omega mod uk p star dx will be equal to integral over 1 by k omega k power p star into n minus p by p mod u of kx power p star dx. So that is equal to integral 1 over k omega. I will take a k power n outside. So if I take k power n outside, I will get k power p star into 1 by p minus 1 by n, which is exactly 1 by p star, sorry. And what is in the bracket is 1 by p star, it will cancel with this p star, so you will just get k, okay, into mod u kx power p star dx. Sorry, this is not into k power n, it is just into n. I am just rewriting the expression like this. Now 1 by p star and 1 by p, that is cancelled, so that just becomes integral over 1 by k omega k power n mod u of kx over p star dx. Now you again make a change of variable, that is equal to integral omega mod uy p star dy, and that is equal to 1. So this proves. So this implies that u k belongs to w1p of omega, but it vanishes outside 1 by k omega, and therefore this implies that uk belongs to w1p0 omega for all k. This, okay, so this 1 by k closure is again, so you can, we have seen this theorem, it vanishes outside a closed set, so you can take the closure also, and therefore it is. So let 1 less than p less than infinity. So uk is bounded in W1P0 of omega, because its mod 1 is bounded, and therefore by Poincare, so this is Poincare, okay, and therefore there exists a subsequence such that, so I will again call it UK. UK converges to some U tilde in weakly in W1P0 omega, because it's a reflexive space. If you have a bounded sequence in a reflexive space, then you have the thing. So now if, and by relic Kondrasov, this converges U tilde in LP of omega. So if W1P0 to LP star were compact, then UK will go to U tilde in LP star omega. But if X belongs to omega for sufficiently large K, X is not in 1 by K omega, implies UK of X equal to 0. So after some level, every point UK of X becomes 0, so this implies that U tilde equal to 0. Since UK converges to U tilde pointwise almost everywhere. Almost everywhere, again for a subsequence. So I am keeping on working with a smaller and smaller subsequence, and therefore you have this. But that's a contradiction. Since mod UK 0 P star omega equal to 1 for all K. So it can't go to 0 in the LP now. Okay, so that proves this thing. We'll continue with this.